I-Rheo is a state-of-the-art software that can be used to simulate various industrial processes using thermoset polymer systems. These processes include filament winding, pultrusion, coatings, and adhesives, and many others. With its highly efficient algorithms and an interface designed for process engineers, users do not need to have any background in math modeling or finite element analyses. In this short video, we show how I-Rheo can be used by engineers to troubleshoot and optimize the pultrusion process. In a typical pultrusion process, continuous rolls of reinforced fibers and fiber mats are impregnated with resin by pulling it through a resin bath or injection chamber. Resin-soaked fibers then pass through a heated die where the resin undergoes polymerization and changes form low-viscosity material to gel and finally into solid hard material. The composite material is pulled out of the die by a puller and then cut to the right size. While the pultrusion process is a simple and continuous process, engineers have to balance quite few process parameters to optimize the process and avoid processing issues. Key parameters to watch are pot life, resin bath viscosity, or the initial viscosity, minimum viscosity of resin as the part moves through the die, position in the die where resin gels, position in the die where the center of the part achieves highest temperature, and final degree of cure as the part comes out of the die. Pultrusion process simulation can help engineers to optimize the process. Process simulation solve kinetic, rheology, and heat transfer equations using finite control volume approach for each material point inside the die. With I-Rheo, engineers do not need any background in finite element analyses or math modeling. I-Rheo, with its state-of-the-art algorithms, solves these equations in no time and provide a visual feedback. First step in simulation pultrusion process is to choose the resin system from the Choose Formulation page. Next, we go to the Pultrusion page and make sure that the material properties are reflective of the fiber and the resin system being used. We then set the pultrusion conditions such as die length, pull speed, die shape, and die width and thickness. Finally, we specify resin bath temperature and die temperature profile. Before we click the Run Pultrusion Simulation button, we specify the material point for which I-Rheo will display the results. We have chosen the material point in between the part surface and the center line. This point can be changed after the simulation as well. I-Rheo solves finite control volume equations in no time. It then displays the temperature and degree of cure profiles of the material point as it travels through the die. Resin must be cured to the desired degree before it exits the die. Initial viscosity, or the resin bath viscosity, is another important parameter. If this viscosity is too high, fibers will carry excess resin resulting into backflow. On the other hand, if it is too low, the part will have dry spots. Note that the graph shows log of viscosity. As the material point travels through the die, its temperature increases. Resin viscosity tends to decrease due to increase in temperature, increases due to polymerization reactions. The minimum viscosity of resin before it gels is a very important factor in determining whether resin will penetrate through the tight spaces between filaments. As resin gels, its viscosity increases drastically, it shrinks. Low viscosity profile and proper gelation position are very important in determining the pull force and surface quality. It is usually preferred that material gels within 30 to 40% of die length. I-Rheo also displays the glass transition temperature profile. As resin cures, its glass transition temperature increases. If the glass transition temperature increases above the material point temperature, polymerization reactions will slow down. In the next example, we compare viscosity profile of two different resin systems under the same processing conditions. From Choose Formulation page, we add another resin system. We then click the Run Pultrusion Simulation button on Pultrusion page. After I-Rheo solves the finite volume equations for both resins. I-Rheo displays viscosity of the material point as it travels through the die for both resin systems referred to as Pull 1 and Pull 2. Even though Pull 2 has lower resin bath viscosity than Pull 1, its minimum viscosity inside the die is significantly higher than Pull 1. Moreover, it gels further into the die than Pull 1. As a result, Pull 2 may have more wetting issues as well as surface quality issues. In addition, Pull 2 resin will require higher pull force than Pull 1. With everything else equal, we'll prefer to use Pul 1 over Pul 2. In the final example, we compare temperature profile of the material point at the middle of the part for two different resin systems under the same processing conditions. We go to Choose Formulation page, remove Pul 2 from the analysis list, and add Pul 3 to the list. Back on the Pultrusion page, we choose the middle point as our material point for displaying the results. After we click the Run Pultrusion Simulation button, I-Rheo solves the finite control volume equations for both resin systems. The max in the temperature profile at the middle of the part must be within the die to avoid cracking issues due to thermal stresses. Resin Pul 3 is more reactive than Pul 1. It can be run at higher pultrusion rates. With everything else equal, we'll prefer Pul 3 over Pul 1. I-Rheo allows process engineers to run Pultrusion simulation on their personal computers. The underlying algorithms are highly efficient and robust. Users do not need to have any background in math modeling or finite element analysis. For further information, please contact Intelligent Support.